Swayam Prabha. Digital India. Educated India.
Since previous lecture, we have started discussing the applications of calorimetry in chemical and biological systems of interest. We also recognized that even though calorimeters have been there since 18th century, but the recent developments in the technology has led to measurements of heats to a very small value. Therefore, it has become possible to address the systems of biological interest in which the heat changes are very, very small. We will now continue our discussion on differential scanning calorimetry in this chapter. As I just mentioned, differential scanning calorimetry is a very powerful technique and a very important technique in elucidating the nature of transitions. Any transition, it need not be a transition in biological systems, for example, in proteins. It could be a solid melting transition, vaporization transition. Calorimetry can be used to address these transitions in a quantitative manner. But in this lecture, let us focus our discussion on micro differential scanning calorimetry, specifically applied to biological systems of interest. And as I mentioned in the previous lecture, that the calorimeters may vary, differential scanning calorimeters may vary from company to company or from requirement based, but the principle of differential scanning calorimetry remains same. Let us take a look at the first slide. The principle of differential scanning calorimetry we discussed in the previous lecture, and what we discussed was the sample of interest is filled into the sample cell, and the reference, which if we are talking about the protein solutions, usually the reference is buffer, and that is filled in the reference cell. Now, since the proteins, nucleic acids are usually very expensive, therefore, one cannot afford for a large amount to be used. Therefore, the different companies are making efforts to come up with the calorimeters with very small cell volume. The cell volumes which require only a few microliters. Today, there are differential scanning calorimeters specifically suited for biological systems, in which the cell volume can range from 1 ml to 300 microliter. And I am sure in future we will have differential scanning calorimeters in which even smaller volume of the protein or nucleic acid sample may be required. And then we talked that what is measured is the differential power, which is added to maintain delta T0 between the cells, and we went on to discussing that when the protein sample is heated, we get a transition. We also highlighted the significance of carrying out a baseline, buffer baseline, which should take care of the heat capacity effects due to solvent and also the geometrical differences between the sample cell and the reference cell. The design of the sample cell and the reference cell can make a big difference. In one of the previous lectures, I showed that in differential scanning calorimetry, usually the size or the shape of the cells is either lollipop type or it is capillary based. What kind of shape should be preferred? If we are talking about the folding unfolding transitions in proteins, and if we are interested in thermal unfolding of proteins, let us recognize that the laws of equilibrium thermodynamics can be applied to reversible systems. And therefore, if we want to ensure the reversibility of the unfolding process, reversibility of the unfolding process, I mean when you unfold the protein and then you lower the temperature, it should be able to fold back. And therefore, if we want to ensure the reversibility, then once the protein unfolds by means of temperature, it should not lead to any aggregation, any form of aggregation. And that is why you do not want the sample to be exposed to a large surface area which should nucleate the formation of aggregation. And in order to attenuate the onset of sample aggregation, the best suitable design of the cell is of capillary type. Let us look at the slide. This is a design which is capillary design, and you can see the cell will have one inlet and there will be another outlet. That means you can fill the sample from one side and it can go through the capillaries, fill the cells, and it can come out from the other side. So, this pair of sample and reference cell of the capillary design is the most suitable for biological system, and that is what is commented over here, that the capillary design attenuates the onset of sample aggregation until after unfolding is complete. I mentioned about the cost of proteins, the cost of nucleic acids sometimes can be very high, and sometimes it may not be possible to buy commercially available proteins. One may have to isolate, purify, and eventually you may come up with a very small amount of protein or nucleic acid. And that is why it is very important to use very small volume of the cell. And this is one way, small volume of the cell, and second is how low in concentration we can go. What concentration do we require so that we can get a reasonable thermal unfolding transition? Let us take a look at the slide. As we can see here, that 400, typically if 400 microgram of the sample gives a very nice unfolding curve. You start from here, you see a very nice shape of the unfolding curve is obtained. And as you keep on reducing the amount of the sample, even 2 microgram of the sample is good enough to at least give us an information on at least very accurately the transition temperature, the Tm, the temperature where heat capacity is maximum. I will discuss more about this. So, this transition is very beautiful, and you see the transition is fairly good. Even if one take 10 microgram of the sample, 5 microgram, some noise starts setting in. Even at 2 microgram, although there is a noise, but at least it is giving an accurate information on the transition temperature. And I am sure if very accurately the area under the curve is measured, then the calorimetric enthalpy can also be very accurately determined. So, that is what I was talking about, that today there has been so much development in the technology that we are able to measure the heat changes associated with very, very small effects. Now, let us talk in details about the protein unfolding. Why do we need to study first of all protein unfolding? When the protein is synthesized from ribosome, we have amino acid sequence which you call as primary structure, and then there is a formation of secondary structure, then tertiary structure, and then in some proteins it may lead to formation of quaternary structure. We discussed about this in the previous lecture. However, when the protein folds, a protein will fold because it is driven by certain intramolecular interactions, and those interactions are hydrogen bonding, ionic interactions, hydrophobic interactions, and few more interactions. Protein folding is a very fast process. You need very fast techniques. However, an alternate method will be that you try to find out what is hiding inside, that what is holding the protein together. That means you unfold the system and try to find out what was holding it together. And that is what differential scanning calorimetry is used for when it comes to study the protein folding unfolding. What you do in differential scanning calorimetry, you heat the sample, you heat the protein, and when you heat the protein, the forces which are holding the protein conformation together start getting weakened, and at some point it will open. And we have to devise the mechanism, we have to design the experiment to find out what forces have been responsible for holding the protein conformation, protein structure together. And differential scanning calorimetry has played a large role in understanding the various forces which hold the protein together. Let us take a look at the slide. In this slide, we are interested in understanding the thermal unfolding of the protein from native state to unfolded state. And let us discuss how differential scanning calorimetry can be successfully applied to study this. Let us consider these ribbons as protein and these colored circles as the buffer molecules. And that is why in the reference you see only you have this colored circle which are the reference molecules, which is buffer actually. And we are interested in studying this unfolding, native to unfolded. So, what you do in differential scanning calorimetry is start heating. You heat both the sample and reference cell at a constant scan rate. And what happens, last time you remember we discussed that what you monitor is power, and power can be converted to heat capacity, and here you see you are plotting heat capacity as a function of temperature. So, when you start heating, we start getting the change in power or heat capacity. And then you see when the transition here, the transition starts and it passes through a maxima. This is the maxima where the heat capacity maxima is observed, and beyond that if you heat, it starts coming back and then the transition is complete. 100% unfolded protein after the transition is over. And you see the ribbons have disappeared, that means the ribbons have been converted to unfolded conformation of the protein. What we have obtained is a heat capacity versus temperature curve, and we have to extract the thermodynamic information from this heat capacity versus temperature transition curve. Let us see how do we get that information. First of all, enthalpy of thermal unfolding. We have thoroughly discussed the meaning of heat capacity and its connection with the change in enthalpy. Heat capacity at constant pressure is defined by dH by dt at constant pressure. You see here we are talking about the constant pressure. When an experiment is designed to be done on a differential scanning calorimeter, it is very important to degas the samples. The reason for degassing the samples is that you do not want any air bubbles in the sample, because in differential scanning calorimetry you heat the sample, and when you heat the sample and if there is air trapped, if there are bubbles in the sample, then the heat capacity will be largely affected, because heat capacity of the liquid and heat capacity of air is very different, and if the bubble come up you will get huge disturbance in your differential scanning calorimetric output profile. And that is why the sample and reference cells of the differential scanning calorimeters are pressurized. You apply additional pressure. There is an internal mechanism of how to pressurize it depending upon where you get the calorimeter from, but the idea of putting the pressure on the sample and reference cell is that you do not want formation of bubbles, that is one, and the second is you are putting a constant pressure over there. So, let us look at the definition of Cp is dH by dt at constant pressure, which I can rearrange and write that delta H is equal to integration Ti to Tf Cp dt. This also we have discussed many times, and I will tell you why I am putting Cal as subscript over here. What we have is we get this kind of, this is the transition curve, and this is the, I would say, the excess heat capacity. Why? I can also call this as excess heat capacity, because you are subtracting the protein buffer scan from the buffer baseline. So, this is an outcome of this minus this. That means, this heat capacity is the value of heat capacity over and above the buffer baseline. So, therefore, if I choose the integration limits, let us say I choose this as Ti and I choose this as Tf, then the value of the integral can be area under the curve between Cp versus, or between Cp and T, or Cp versus T, within the limits Ti to Tf. And that is what is shown over here. If I choose this as Ti and this end as Tf, then the area under this curve within this baseline and the overall heat capacity versus temperature curve between these two limits will be equal to delta H, and Cal subscript I am putting because this is calorimetrically determined value of heat capacity. There is no assumption in this. What you are, let us look at the slide, what you are getting is it is a completely experimental curve with no assumptions made, and the area is the calculated area with no assumptions made. Therefore, this delta H is the true enthalpy of unfolding, and let us label this as delta H Cal, calorimetric enthalpy. And I will soon discuss with you that why there is a slope associated in the beginning and why finally also you see some slope, and why this heat capacity variation and this heat capacity variation do not have the same slope. Why the slope differs? Why the heat capacity here is higher than the value of heat capacity? These all we are going to discuss in the future lectures. But let us continue our discussion on what parameters are available from this complete differential scanning calorimetric output. This is the output Cp versus T, and I just discussed with you that how do we get calorimetric enthalpy. This is area under the curve, and if the transition is symmetric, then the midpoint is either called Tm or it is called T half. Why it is called Tm and T half, I will discuss with you in details. In one of the previous lectures, you remember I labeled this as Tm, that is the temperature where heat capacity is maximum. Now, we are talking about this reaction, native to denatured reaction. You are heating the protein from the native state and taking it towards the denatured state. And then at T half, that is at this temperature, transition is half complete. Because if you consider this complete peak associated with the complete transition from native to denatured state, then at a point where the area, this total area is divided into two equal halves. I repeat, where the area is divided into two equal halves, that temperature is T1 half. Let us remember this, and that is what is commented over here, that at T half the transition is half complete, and if this transition is symmetric, please note this, if this transition is symmetric, then the Tm, that is the temperature where heat capacity is maximum, will be same as T half. That is what is commented over here. For two state symmetric transition, Tm is equal to T half. Now, let us write down an equilibrium constant for this process, n going to d. So, we are talking about this equilibrium native, if I write as n, in equilibrium with denatured protein, I will write this as D. Then K I will write as the concentration of D divided by the concentration of N. Now, at T equal to T half, that is where reaction is half complete. When the reaction is half complete, then both these concentrations will be same. Concentration of D will be N by 2, this will be N by 2. At T equal to T half, K will be equal to 1, because both these concentrations will be same, and delta G naught, which is equal to minus R T log K, will be equal to minus R T log 1. Log 1 is always 0. We get that delta G naught is equal to 0. Let us take a look at the slide. This is what I was talking about, that when transition is half complete, the value of equilibrium constant for this two state transition is 1, and obviously the delta G naught will be equal to 0. And this information, that delta G naught at transition temperature T half, let us remember, we will call this as transition temperature. If delta G naught at transition temperature is 0, we will use this information extensively in getting the temperature dependent thermodynamic quantities, especially related to the folding unfolding processes in proteins. And you see, I am also writing here delta H Vent half. We can get Vent half enthalpy. How do we get Vent half enthalpy? Vent half enthalpy can be obtained if I can express equilibrium constant as a function of temperature. And suppose if I integrate this differential scanning calorimetric curve, you integrate, the integrated plot will look like this, right. So, let me go back here. If the integrated plot, let us say, I will put as property the integrated one, temperature, and if the variation is like this, then let us talk about these distances. If this is native state, this is denatured state, then this whole distance, because here complete denatured, protein will be complete denatured, therefore, this whole distance I can write proportional to concentration of denatured state. And therefore, if I draw a line over here at this temperature, then these distances can be approximated or will be proportional to, this is concentration of denatured state, this is this much protein has denatured and this much protein native is still. So, this one I can approximate by concentration of native state. And that is what is seen in this slide, that if I know D and if I know N, then let us take a look at here. If I know D, if I know N, then I can write K is equal to concentration of D over concentration of N. Remember, we are talking about N going to T. and this K can be obtained at any temperature between this limit and this limit. We can get temperature dependence of K. Let us go to slide, and if I have the temperature dependence of K, I can get Van 't Hoff enthalpy. And this Van 't Hoff enthalpy depends upon the shape, that is why the arrow is pointing out on the shape of the DSC curve, because the integrated form, the shape of the integrated form will depend upon the shape of the differential scanning calorimetric output. And Van 't Hoff enthalpy, that is Y, which is obtained from the temperature dependence of equilibrium constant, will depend upon the shape and hence will depend upon the shape of the differential scanning calorimeter. And the difference in the heat capacity of denatured state and native state is delta Cp, change in the heat capacity. Delta Cp can be calculated from Cp denatured minus Cp native. This delta Cp is also very important and gives lot of information that we will discuss in future. So, the question is, why calorimetry? Calorimetric enthalpy and Van 't Hoff enthalpy provides information on mechanism of folding unfolding transitions, and from the differential scanning calorimetric curve we can get calorimetric enthalpy, we can get Van 't Hoff enthalpy, and the ratio of the two provides information on mechanism of the unfolding process. So, you see what we have started now appreciating, that not only we are getting the numbers, but we have started connecting the information which is available with the mechanism. So, in this lecture what we discussed is how to obtain these quantitative thermodynamic parameters associated with the protein unfolding, that is transition temperature, calorimetric enthalpy, Van 't Hoff enthalpy. And now we have started appreciating that the calorimetric enthalpy and Van 't Hoff enthalpy comparison can give us information about the mechanism of the unfolding process, and this we will discuss in details in the next lecture. Thank you very much.